Alright, welcome to Math 330, Chapter 3, Section 3, Higher Order Differential Equations. So today, this podcast will help you determine, or help you figure out how we can find the solution for a higher order differential equation. So what is a higher order differential equation? This is one. It is a second order because the highest derivative is a second order derivative, and we have coefficients that are dependent on x, and then you have this function f of x. So the differential equation is equal to this function f of x. By definition, this is the most generic form you can have for a second order non-homogeneous differential equation. It is still linear because all the derivatives and all the functions of y are still linear terms. What kind of coefficients could we have? This is an example of the type of coefficients we can have. Now, we're not going to start out solving one like this, but I just wanted to know what one looks like. What does a nonlinear differential equation look like? This is a nonlinear. So there's a nonlinear term here for the first derivative. There's a nonlinear term here for the function y, and there's a nonlinear term over here that's y times the second derivative. This makes it a nonlinear higher order differential equation. Now we can go higher than a second derivative, but mostly the ones you're going to solve are just second order differential equations. What we are going to learn to solve is homogeneous second order differential equations with constant coefficients. Our coefficients will be constants. And you notice this function f of x is now 0. This is what makes it a homogeneous differential equation. And what we're going to do is try to find that. I'm going to claim that y1 is the solution to this, and y2 is the solution to this. So if I have two separate solutions, then the principle of superposition says if I add these two solutions together, multiplied by some coefficient c1, some coefficient c2, this is also a solution. Now, what also has to be true about y1 and y2 is that they have to be linearly independent of each other, which means y1 cannot depend on y2 or y2 cannot depend on y1. So, how do we know that these are solutions? So here's a differential equation right here. The second derivative of y minus the y equals 0. And I claim that y1 and y2 are solutions to this differential equation. How do we verify it? Well, it's quite easy. We have to plug them back into the differential equation. So I need to take the second derivative of e to the x and subtract off e to the x. What do I get? Well, what's the second derivative of e to the x? Is itself there, so itself minus itself will equal 0. So that's a valid solution. How do we do the second one? The same way, we plug it in and take its derivative. You take the first derivative, it'll give us a minus sign out front. You take this derivative of that, it gives you another minus sign, two minus signs to the plus. So this will be plus e to the minus x minus e to the minus x. So this is also equal to solution. So the sum of those two solutions should also be a valid solution by the principle of superposition. So you can also have some initial conditions to help you solve. In order to figure out C1 and C2, you need two initial conditions. The initial condition for the function itself and initial condition for the derivative evaluated at some point. So knowing these two, we can find C1 and C2. So what I do is I plug in what the value of the function is at x equals 0 and y has to equal 0, so we get this expression. So if I solve that, I get C1 equals minus C2. And now if I do my derivative, I have to take the derivative first. There's the derivative of my solution. And then I plug in what it needs to be in order to get it. And so I have this expression. This tells me I have 5 is equal to C1 minus C2. I know what C1 has to equal. It's a minus C2. If I plug that in there, I can solve for C2 now. C2 is a minus 5 halves. I plug that back into C1, it's 5 halves. So my particular solution, or a single solution, is equal to this. This actually is a family of solutions. Depending on what the coefficients are, I get a whole range of solutions. This is one particular solution where this solution goes through 2 points that I'm looking for, forces the function to go through 0 at x equals 0, and forces the derivative to go through 5 at x equals 0. And that gives us one particular solution. Let's try another verification. Let's try this differential equation. So here's my y1 and y2 and my initial condition for my velocity. I plug in my first y1 function. I get this expression. I take the second derivative of this function. I get this value. I take the first derivative. I get this value. You see I have plus, I have one factor here and one factor here. That gives me a positive 2e to the minus 2x. Subtract off a negative 2e to the minus x, and then I get 0. So y1 is the solution to this differential equation. Let's try y2. I plug it in. This is my y2. Now this derivative is going to be a little more because we're going to have to use the product rule in order to solve this. And so if I take the second derivative of this, let's do the first derivative first. So if I take the first derivative of y2, I get this. And then if I take this derivative again, I get this expression. And so let's see if this equals to 0. I got a positive, a negative 2e to the minus x. Here's a positive. Those will cancel. I have a factor of x e to the minus x. Another factor of x e to the minus, so that's 2 positives. And I got 2 negatives here, so they add to 0. This is indeed a solution. Let's find out what coefficients C1 and C2 have to equal to satisfy these conditions. To do that, I plug in the value of the function at x equal to 0, and I get C1 is equal to 2. I have to take the derivative of my solution, so this is the derivative of my solution. And then I'm going to plug in the value for the derivative at x equals 0. I'm also going to plug in what C1 is. Since I know what that is, I'm going to plug that in right here. And this allows me to solve for C2 now. And C2 is 1. So this is my particular solution for this differential equation. This would be a family of solutions. Alright, so you have to guarantee that you can get one unique solution to the differential equation you're going to solve, and that solution has to exist, and that solution has to be unique. And to do that, if I have this type of differential equation, my solution will exist on a particular interval and be unique on that interval if I have an initial condition for the function and a initial condition for the derivative of that function. And so then I can find my solution right here after finding my y1. This should be y2. I apologize for that error. Alright, how do you know if y1 and y2 are going to be linearly independent? Well, to do that, we have to use an idea called the Wronskian. It's basically if you have two functions, we'll call them f and g, and you want to check to see if they're linearly independent, you use the Wronskian. What is the Wronskian? Well, You set up a matrix of function f and function g, and the derivative of f and the derivative of the g. What is the Wronskian? The Wronskian is the determinant of this matrix. So I find the determinant by multiplying this function times this, and subtracting off this function times this. This is the expression I get here. Well, what does this have to be linearly dependent or linearly independent? If the Wronskian value equals 0, the functions are linearly dependent, and these two solutions, and this would not be a solution to the differential equation if that was true. You'd have to do some trick to make sure that one of them was independent of the other. And so to find linearly independence, the Wronskian does not equal 0. So let's do a few examples of determining if functions are independent. So here's my f, and here's my g. This just happens to be a solution to the differential equations we did earlier. And so here's the derivative of f, and here's the derivative of g. I find the determinant, which is this. And so what I want to do now is take my, simplify this, and if I do, I get this expression right here, and that is not equal to 0. Let's try these. This is my f, this is my g, my derivative of f, my derivative of g. We take the determinant of that derivative, and we get this function. I factor out a minus sign. I get sine squared plus cosine squared, which is 1. So the Wronskian is equal to minus 1 and is not 0. So these set of functions, sine and cosine, are linearly independent, and e to the minus x and x e to the minus x are linearly independent. Alright. How do you find a solution to this homogeneous second-order linear differential equation? Well, what would be nice if we had a function of a solution for y, but if we took the derivative, this function would show back up. So, do we know a function like that? I think we do. Let's say I choose the solution right here to be e to the r times x. I have no idea what r is, but if I take the derivative of that, I would get this, r e to the rx, and if I took another derivative of that, I get r squared e to the minus rx. So if I claim that's my solution for y, and then plug it in here, take my derivatives, and then factor out the exponential function, I get a polynomial of r times my exponential function. Well, that has to be equal to 0. This left-hand side here has to equal the right-hand side. Well, e to the minus e to the rx is only 0 if this term gets negative and gets a large negative number. And so the only way I can guarantee to make it go to 0 is to make this polynomial 0. So I need to find the roots of this polynomial. If I find the roots, I use the quadratic equation to find the roots, and I can find two distinct roots. Now, the trick to this is this discriminant right here. So let's look at this discriminant. Well, this discriminant can have three particular values. It can be larger than 0, and if it's larger than 0, I get two distinct real roots. So I get an R1 solution and an R2 solution. If it can be equal to 0, if it's equal to 0, I just get one repeated root. I get the same root repeated. And the last one is, if this is less than 0, I would get two distinct complex roots. So I'd still get an R1 and R2, but they would be complex. So what we're going to do is talk about the first two cases today. Repeated roots, repeated real roots, and two distinct real roots. Let's do an example. So here's your differential equation. I'm going to plug in my guessed solution. I'm going to solve for the polynomial. Again, I got to make this polynomial equal to 0, so let's find the roots. And if I solve for those roots, I get these two values for r. Now see, these two values are repeated, so this is a repeated root case. So I have to handle that somehow. I have to come up with two linearly independent solutions, because if I plug these r's back in, I would have two of the same exponential. So what I'm going to do is, so here's my first solution. Let's say my y1 is right here. I plug my root back in. I got this one. And here's my second one. And to make it linearly independent, if you have this case of repeated roots, you have to multiply by a factor of the independent variable for every case of repeated roots. So I can use it once. If I use it again, because I have to, because I have a repeated root, I have to multiply by a factor of the independent variable. If I was doing a third order differential equation and the roots repeated 3 times, I'd have to multiply by 2 factors of x to get a linearly independent equation. And so this is my solution. Well, let's check to see if it is my solution. To do that, I have to plug it back into my differential equation. So I'm going to have to take the second derivative of this and the first derivative of this. So let's do that. If I take my second derivative, I get this expression. And if I take my first derivative, I get this expression. Well, is this going to be 0? Well, let's look. Let's look at all the expressions that have a factor of x in it. Here I have 4e to the 2/3 x times x and a C2 coefficient. Here I'm going to have a minus 8. Over here I have another 4. So I'm going to have 4 and 4, that's 8. I have a minus 8 here. That adds to 0. Okay, let's look at this case right here, the C2 coefficients. I have a 3 times a 4, that's a 12. I have a minus 4 times a 3, that's a minus 12. They're going to add to 0. And let's look at C1 now here, and the C1 here. I'm going to have a 4. I have another 4 over here, that's going to add to 8. I'm going to have another minus 4 and a 2, that's minus 8. So that minus 8 with the positive 8, I'm going to add to 0. And I'm going to get 0. I'm going to get 0. So this is a solution. Alright, so let's have an example. So here's a differential equation we need to solve. So I'm going to plug in my generic solution here. I have to do all the derivatives, the first derivative and the second derivative, and group them together into this form. Now I got to get the left-hand side 0. The only way to do that is make this polynomial 0. So I need to find the roots of this polynomial. The values of r that makes this go to 0 is a minus 1/2, and it shows up twice. I have 2 of them, so it's another repeated root. So my solution would be, here's my generic solution with r of 1/2 right here for the first one, and here's the second one, r of 1/2. Now since it's repeated, I have to multiply again by another factor of the independent variable, in this case x. So this is going to be my family of solutions for this differential equation. And what I need to do now is verify if the solution is correct. And the way I need to do that is I've got to plug it into my differential equation. So I got to take the first derivative again and the second derivative. Students always ask me how I can do my derivatives so fast. Well, it's because I had to do this a lot when I was in your place. And so let's plug it in. Let's plug in the second derivative here. This would be your solution for that. Let's plug in the first derivative. So this is going to be the solution for that. And let's see if it adds up for 0. So let's look at the terms multiplied by x. Okay, let's look at the terms multiplied by x. So here I got just an x, no coefficient. Here I got a 2, a minus 2. Well, here I got another x right down here. It's got a C2 coefficient. This has a C2 coefficient. So those are going to add to 0. Let's look at these C2 terms here. I got a minus 4. I got a minus 2 and a minus 2 here. That's a positive 4. So those are going to add to 0. Let's look at this coefficient here. That gives me one term of this. I come over here, I've got minus 2 terms. So I have basically added to this one, I get a minus 1. And then I have another minus 1 term right out here, a plus 1 term. So those are going to add to it. So this is a solution to the differential equation. Let's try another example. So here's a third differential equation right here. How do I solve that? Well, I plug it in my generic solution, right? I take the second derivative of it. I take the first derivative. The second derivative is going to give me a factor of r squared out front. The first derivative is going to give me a factor of r. So I get this expression right here. I get this polynomial times my generic solution. I've got to make this whole thing equal to 0. So the only way to do that is make this polynomial equal to 0. So I can factor these roots out. And I factor these roots out. Well, I get 2 real roots. These are 2 different roots. They're 2 real. So I get a y1 and a y2 solution. Let's plug it back in. Here's my y1 solution. Here's my y2 solution. And I have my 2 unknown coefficients. So this is my family of solutions right here for this differential equation. To find C1 and C2, I'd have to have some initial conditions, which I don't have for this differential equation. Well, let's verify its solution. Let's plug it back in. Let's do its second derivative, and it turns into this. Let's do its first derivative, it turns into this. Let's validate. I have this expression here, and this expression, it's a minus sign. So this is going to come out to be 40 divided by 2, or 20, a positive number. We've got a negative 20 over here, so they're going to add to 0. Let's look at this expression and this expression. If I add these together, what are they going to be? I got 28 and I've got 32, so that's going to be 60 divided by 3 is 20. It's a positive 20. I got a negative 20 here. They're going to add to 0. So I've got another solution here. Alright, one more time. How do we do this? Well, I have my differential equation. I plug in my generic solution, and I do the derivatives. This is going to give me a factor of r squared. This is going to give me a factor of r out in front. I factor out the polynomials. I get this expression. And then I got to make that polynomial 0 to make the left-hand side equal to the right-hand side. I have to find the roots. So if I find the roots, I get 2 distinct real roots here. I get 3/5 and a minus 4/7. What's my solution going to be? Here's my y1. Here's my y2. And then this gives me my family of solutions for this differential equation. Well, let's verify to see if it's correct. I have to plug this back into the differential equation to see what it is. Take its second derivative, take its first derivative. If I take its second derivative, I get this expression. Yes, you're probably going to have to take a while to verify if this is correct, but I recommend you try and do it, and yes, you can do it. It will take you some time, but you can do it. Let's do the first derivative. So this is the first derivative. Let's see if they add up to 0. So I got, here's my e to the 3/5 x, right? I add that to this one, which is a negative 3/5 here, and that gives me 60 over 5. Well, 60 divided by 5 is 12. It's positive 12. I got a negative 12 over here. It adds to 0. Let's look at this expression here, and I add it to this one. That gives me 84, and 84 divided by 7 should give us 12, a positive 12, and I got a negative 12 here, so it adds to 0. So I hope you enjoyed your first exposure to solving second order differential equations. The whole idea is to get this expression right here. This is called the characteristic equation. Once you have the characteristic equation, you can solve for the roots. And we've talked about two cases. We've talked about a repeated root case and two distinct roots. I'll see you in class tomorrow. Bye.